So last week we had a look at some logic gates, and out of those logic gates came a number of logic functions that you could put together from those gates. Well, we were using a lot of symbols that look a bit like algebra, and hence this leads us to this little section on Boolean algebra, which is the kinds of operations you can do on those logic functions. So we had a plus symbol to signify saying that we are doing an OR operation between two variables, and we had a dot or no symbol between two variables if we're doing a multiplication or an AND function. And we'll see that these work pretty much as normal algebra does, and also most of the operations will work too. So we'll just have a quick look at those and introduce a very special operation devoted to Boolean algebra. Okay, so what we're going to do is we're going to learn to apply Boolean algebra to simplify logic circuits. So first thing is, why is this useful? Why are we learning Boolean algebra? Well, it turns out that, as we saw on Thursday, any logic circuit, well, most logic circuits can be represented in a number of ways. Sorry, let me rephrase that. Most logic functions can be implemented in a number of different logic circuits. So we saw that two different circuits could give the same exact truth table on the output, and those are equivalent. So given a choice, it's often best to choose the circuit which has less number of gates. So remember some of those circuits had a number of gates, there was one circuit which had 2 gates and one circuit which had 3 gates, but they gave the same output. So if that's the case, why not choose the one with less gates? So Boolean algebra will allow you to transform something with lots of gates to something with less gates. We're going to cover a number of advanced logic gates. So up to this point, we've only looked at AND gates, OR gates, and NOT gates. Okay, and they had a number of different symbols. And the inverter here. Well, there are a number of other gates which have very specialized uses, and we'll see those. And one of these is the NAND gates. And what we want to see by the end is that all of these basic logic gates can be represented by NAND gates, and we'll show you, we'll prove that that's the case. And the good thing about this is, if you can prove that any function can be implemented in AND or NOT gates, and you can prove that these can all be implemented by NAND gates, well, it makes it a lot easier to build circuits in practice. Okay, so previously we looked at all those standard gates, and we saw that 3 input logic gates could be made from a number of 2 input gates and if you attach logic 1s or logic 0s to gates, so we had the case like this, where you attached a 1 here or a 0, you would get a number of different functions out. And we used the truth tables to prove this. So we said that if the truth table for 2 different arrangements of gates were the same, then those functions are exactly the same. And finally, as I said, we express these in a number of functions, and the things we can do to the functions is called Boolean algebra. Boolean algebra was named after George Boole, unsurprisingly, as most of these things in engineering are. And just as a recap, here are the symbols we use for the operations. So plus was an OR, dot was an and this prime, or this bar above a variable, was used for NOT. So, as we saw, most of the rules can be expressed using truth tables, but here are some laws which we saw and summarized when without those gates. So before, we had a gate here. Oops. We had the OR gate, and we said that if I put A or A into here, then the output was just going to be A. And that's summarized in this rule. Okay, now these are the other rules summarized just in Boolean algebra form. So for an OR gate, here's a rule. If you take a variable or its opposite, then it's always going to be 1, which makes sense, right? Because if this is 1, this is always 0, and for an OR function, this will always be equal to 1, no matter which order you do those. Now all of these we sort of worked through last Thursday, so these aren't that interesting. Okay, so just have a quick look at those. Now have a look at this one. So here's something that we take for granted in normal algebra. This is called the associative law, and it says that it doesn't matter which operation I do first when I have 3 variables. If I do an OR operation between all of them, well, the output's going to be the same. And in fact, this is equal to A plus B plus C. So in this way, this is saying this circuit we could represent by an OR gate with A and B, and then we do another OR gate. Oops. We do another OR gate here with C. Okay. And this one we represented by having the same thing, except this was B or C, and the other input was A. So these are equivalent. Okay, and this is called the associative law. We all know this one. Boolean algebra also follows the distributive law. So this is where you multiply a variable by something in brackets, and that, in this case, the thing in brackets is an addition. So over here, you've got A plus B, so A or B and C, and what happens is you can do the same thing as you do in normal algebra, which is you multiply AC to give us this one, and you multiply BC to give us this one. So that also works. So this says, so over here, in this case, just to refresh, if I were to implement this function using logic gates, then I would need an AND gate for the AC, right? And I would need an AND gate for the BC, and I would need to OR these together to get AC plus BC, right? In this case, all I need is an OR gate with AB, and then one AND gate with C, and this gives us A plus B or C. Now, if you have a look at the left one, there's only 2 gates required. If a gate costs 1 cent, then this circuit costs 2 cents on the left. If you look on the right, you need 3 gates. So if a gate costs 1 cent, you need 3 cents to construct this circuit on the right. So even though these two are equivalent, it's not necessarily obvious when you look at the functions. But Boolean algebra allows you to show that these are. Okay, and here's a couple of Boolean algebra specific laws. Now these laws don't apply in normal algebra. Okay, there's no such thing as these laws in normal algebra. And what this says is that if I have an AND gate, so over here, if I have a function A and B and C, then it's actually equal to the opposite of, so what we do is we invert all the variables. We change the AND gate to an OR gate, and then we take the inversion of all of that. And these are actually equal. Now, you say, when would you ever use that? So the reason I'm showing you this is this leads us directly, we'll see shortly, into a method in which we can transform all of these gates into one type of gate, a NAND gate. So this can also be written as if I take A, B, C and I invert it. So I'm taking A, B, C and I say, okay, we'll put an inverter on the outside. So what that does is essentially say we do this and we do this. So you take a double knot, then this equals A plus B plus C. There's a similar result for if we look at OR gates. So if I take A or B or C, and I take a knot on both sides, so these two knots cancel, then you get not A times not B times not C. Okay, so these are De Morgan's laws. So the easy way to remember this is if I have a gate, it's an AND gate or an OR gate, you take the inversion of it, you swap the gate and change the input and invert the inputs, and that'll be the same. Okay. Okay, so here are just some proofs of this. Now it's easy to prove for 3 variables because in 3 variables we only have how many rows? 8. What if we have 4 variables? How many rows will our truth table need? 16. What if we have a computer with 8 bits? You need 256 rows, right? So for each increase in variable, the truth table gets a lot larger for us to prove equality between them. So in a way, this shows us the limitations of truth tables. So truth tables are well and good when you've got low numbers of variables because you can just write out all combinations of the variables. But when you start getting lots and lots of variables, and you do when you design anything, when you design a real computer, you can't really use this method anymore to prove equality. So you can prove equality otherwise by using Boolean algebra. But as we'll see, when you're using Boolean algebra, it can get a little bit hairy when you're actually doing the calculations. Okay, so this is this is the associative law, A plus B in brackets plus C is equal to A plus B plus C in brackets. Here's a distributive law. So here, this is A plus B times C equals AC plus BC. And I've shown each of those columns here, AC, BC. And if we work those out, they come in the same. I think that's written down in your notes, so I won't go through it. Okay, here's De Morgan's laws. These are the interesting ones. So we've got ABC, and we're saying that that's equal to, we invert all the variables, change the gate, and do an inversion of everything. So over here are the inversions of all the variables. And if we take an OR of these, so you can see that all of these rows have 1 except for the last row because that's not A or not B or not C. And if we take an inversion of that, which is here, then this becomes all 0s and 1. So all 0s here and 1. And if you just look at the row, if we just look at ABC, well, ABC is only 1 when all of A, B, and C are equal to 1. Okay, so this is just the empirical proof of De Morgan's law for the AND gate. And for the OR gate, there's a similar result. Over here, you've got not A, not B, not C. So they're just inverted ABCs. And if we take A plus B plus C, then everything's 1 except for this row. And if we take now on this side, we take not A, not B, not C here, then that's only true when these rows are 1, which is here, and then we take the inversion of that to give this, and that gives us that these 2 rows are equal. Okay? Equal. Okay, so there's a couple of practice questions in the tutorial, but that's pretty much all we'll deal with in terms of getting you to use De Morgan's laws. But they help us to explain something a little bit later. Okay, so here's an example of where we would use something like Boolean algebra. So you're given this circuit. We've got 3 variables, A, B, and C here. And we want to find out what Q is. But we want to, well, firstly, we should figure out what Q is in terms of the gates, and then we want to use Boolean algebra to minimize the number of gates that this circuit requires. Okay, so we can do that. So if we look at the first gate, AB here, right? So this is A and B, so it comes up in red. The next gate here, oops, sorry. The next gate here is B or C, because you've got B coming in here, or C coming in here. So it gives us B or C. The next one gives us B and C. So over here you've got B and C, giving us B and C. Okay, so far so good. Then what comes out on this output, on this one, we get B or C ANDed with B and C. So that's this one. And finally Q, our output Q will be equal to, now this OR gate takes in the values of A and B, which is here, or the stuff over here. Okay. Okay, so here's our function. A and B plus BC times B plus C. How do we simplify this? Okay, now there's many ways you could do this, and often you'll find that the answer is not unique. Okay, so let's have a look. So here's our function, AB plus BC times B plus C. What could we do? Well, we could use the distributive law. So over here, you've multiplied through BC on both sides, and so this is BCB plus BCC. Okay. Then you've got over here, using the fact that A times A is just equal to A. So if I've got over here, you've got C times C, well, that's just equal to C. And over here, you've got B times B, and that's just equal to B. Okay, so you're getting rid of variables that we don't need. Okay, just we're doing algebraic simplification, so we're really collecting up the terms there. So in normal algebra, if we have two A's, if we have A times A will be A squared, but in Boolean algebra, because A can only be 0 or 1, A times A can only be A. Next, we use the fact that if I have B, C, or BC, so use the fact that you've got A or A, well, that's just equal to A, which means that BC plus BC must just equal to BC. And what else can we do? Well, we can factorize out the B using the distributive law again. So you're taking the B's out and having A plus C in brackets. Okay, so here's our simplified circuit. So all of this can be crunched down to an OR gate for this A or C and multiply it by a B, multiply it by B here. Okay, and so Q is equal to B and A or C, and these two are actually now equivalent. Okay, so why don't you guys, oh well, in a second you guys can have a go. But just before we do that, just wanted to show an example of De Morgan's laws. So if I have an OR gate, if I have an OR gate and I have A or B or C here, so we're saying that this is equivalent to this. Okay, this is not A, not B, not C. Okay, so interesting thing happens here. We're saying that this arrangement on this side can be replaced by a whole load of NOT gates and changing the gate. Well, what's the only difference? Well, I don't actually have to change what's happening outside the box here. All right? So these two are actually equivalent. So it turns out that there is a name for this kind of gate, which is an AND gate followed by a NOT gate. Okay, and this is often abbreviated to this kind of symbol, and this is called a NAND gate. Okay, so as the name suggests, it's a NOT AND gate. And if we just invert all of the inputs, right, then this is the link between the two gates, which is given by De Morgan's laws. So De Morgan's laws came up with this result. If we implement this result in logic gates, then we start to be able to turn this into something called a NAND gate. And it turns out that the NAND gate is going to be gives you exactly the same if we invert all the inputs. Okay, so you've got A, B, C here. If we invert all the inputs, A bar, B bar, C bar, then it turns out we can invert the inputs, put it into a NAND gate, and we get exactly the same function out. Okay. Now, if I can do this with an OR gate, turn it into a NAND gate, and if I'm able to use a NAND gate to represent the other two gates, then I'm able to use NAND gates to represent all gates, and that makes things a little bit easier for us, which I'll show you very shortly. Okay, so here's the example. Please have a go at this and use Boolean algebra to simplify this function. So this might take a little while. I'll give you a few minutes, probably about 4 or 5 minutes, because it can be a little bit tricky. Okay. So you may need to use all the laws that you've just seen. Okay, so who's written more than 10 lines trying to work this out? Okay, who's written about 5 lines? Okay, interesting. It's not as easy as it looks. Is the thing that this question is trying to show. Okay, so give you 1 more minute, and then let's work through it. You think, hey, this is a good thing that would be solved by a computer. Oh, hang on. To construct a computer, I need to do this kind of thing. Oh. All right, last chance, if you're going to put anything in melts. Look over at your neighbor and go, what did you put? All right. 5, 4, 3, 2, 1. Anyone? Is that it? Everybody? Okay. All right. What did we get? Oh, by the way, has Jamie played this yet? He hasn't? Oh, okay, maybe I'll play it in the next lecture. All right. Okay, so what were we doing? We're doing 6.1, weren't we? And the winner is, not as clear-cut as usual. We have D, which is A prime, but we also have a number of people on all the other ones. Okay, so, which is about what you'd expect because this is not the easiest of things to do. Okay. Now this is going to look easy because I made the question and I know the solution, so I know which steps to take. And even then I might get it wrong. Okay? Okay, so what I would do, because I know the question, is I would go AB prime, I'd leave that one the same, and then I would multiply out these two. I would go A prime, B, oh actually, no, sorry. See, even I stuffed this up. Easily, an easier step would be to go AB prime times A prime plus B times, now what's this equal to? 1, all right, times 1. Yeah? So if you started multiplying out A prime B, B prime, A prime B, that would be perfectly correct, but would make things a lot harder. Okay, so what's the next step? Well, what we could do is we could notice that this thing is, so what you might think now, why don't you use the distributive law and you go A, B prime A plus AB prime B. You could do that. It starts to get messy because you start having 2 variables under 1 inversion over here, multiplied by 1 variable under 1 inversion, and same over here. So there's no easy way you can combine things by doing this. So I would suggest another way to do this is you would use De Morgan's law on this one. So anytime you've got multiple variables all inverted, you can use De Morgan's law. So this would be, so we invert the individual variables and change the gate. Okay? And this gives us A prime plus B. And this 1 has disappeared because it's multiplied by 1. Now you can go through and do your multiplication out or distribution. And so this is A prime A prime plus A prime B plus, what are we up to, B prime A prime plus B bar B. Okay, so what is this equal to, this first one? Just A prime, because it's A prime and A prime. Plus, now you've got A prime B, can't do much with, and you've got plus A prime B prime, plus, what's this one equal to? 0. Good. Now, this is equal to A prime. Now we can use the distributive law again in the reverse direction. So now you can collect up in brackets 1 plus B plus B bar, right? So we've taken out all the A primes. Now 1 plus anything is equal to what in an OR gate? 1, all right? So that's equal to 1. So we're left with equals A prime times 1, which is equal to A prime. So the answer is D. Congratulations. But you can easily see, if you went on any other step, that this can get kind of messy and you could get the wrong answer. So it is quite tricky, which is why we like having computers to do this if you've got lots of variables, because imagine trying to do a 6-variable one by hand. It would be crazy. Okay, good. All right, we're just going to finish off looking at what these advanced gates that I've been telling you about are. So we sort of know what a NAND gate is. So a NAND gate is an AND gate with an inverter directly after the output of the AND gate. Hence it's called not AND or NAND. Okay. Here's the truth table for a NAND gate. So it's basically it's an AND gate with a 1 where the zeros are and the zeros where the ones are. So just to contrast that, if that's A and B, this would be 0, 0, 0, 1. Well, a NAND gate is 1, 1, 1, 0. Okay, so easy enough. Here's what I showed you before, where if I have a NAND gate and I invert the input variables that go into the NAND gate, all that comes out essentially is an OR gate. Okay, you can prove this. So this is not A, not B. So it'd be 1, 1, 0, 0, be 1, 0, 1, 0. Right, so not A, not B, inverted. So this would be A, B. So you would get 1, 0, 0, 0, and then I would get A, B, all inverted, which is what this is. And this would be 0, 1, 1, 1. Okay, so De Morgan's laws tell us that we can convert an OR gate into a NAND gate simply by inverting the input variables. Okay. Now that doesn't sound like anything very profound, but shortly you'll see that it is. Before we get there exists. So what you start to notice here is that anything that you can do with an AND, there's some sort of analog, well, there's some sort of analogy that you can have with the OR gate. Same thing here. So here's a NOR gate, which is a not after an OR gate. So here you've got the OR gate with a not after it. So that circle represents an inversion. And what you get is, so here you get A or B. And A or B would be 0, 0, 1, 1, 1. And then if we take the inversion of that, we get F. Okay, so you take not A or B, gives you F. So it turns out that this, in a similar way, you can convert an AND gate into a NOR gate. So I won't show it here, but it's pretty much the same thing as here, except you replace the AND gate with an OR gate and change the symbols. So that's a NOR gate. Why is this useful? It turns out that when I show you that any gate can be made out of a NAND gate, or any function can be made out of a NAND gate, you can do the same with NOR gates. Depending on which one you use to implement your logic functions, has implications for how fast a particular circuit can be, and has implications for how much power each of these might consume. So you might want to use a NOR gate for some applications, you might use NAND gates for some applications. Here's a special gate called an XOR gate. The X stands for exclusive. So this is, you need special drinks cards to get into this club. It's an exclusive OR gate. And it's an OR gate with a double line on the input. Okay, and here is the special symbol for the exclusive OR gate. It's an OR symbol with a little circle around it. So the exclusive OR gate is 1 when two inputs are different. So it's a 1 when either one of the inputs is a 1 and the other is a 0. So it's exclusively if A is a 1 or B is a 1. Okay? So the 1s here are it's only a 1 on the output if these two are different. Now, where would you use this? It turns out you use this in binary addition. So if I look at this is really just binary addition for the bit here, F. So if I've got a bit A and a bit B, they could be 0s or 1s, and I want to add them together. What is the sum of that? Well, you can use an exclusive OR gate to give you the sum, because 0 plus 0 equals 0. If either of these is a 1 and the other is 0, then the sum would be equal to 1. If both of them are 1, so this represents the case where you've got 1 plus 1, then the carry bit, the sum bit here would be 0, right? And you would need to have a carry bit. Let's say here, this is the carry bit. Yeah? So that's the case where you've got 1 plus 1 equals 0. So that's where you could use an exclusive OR gate. Finally, another one that we're showing is an exclusive NOR gate. So this is an XOR gate with an inverter over it. We don't use this one very much. This is more just included for the sake of completeness. But you can use this to check if two inputs are the same. So the output of this is a 1. So the output of this gate is a 1, which is F equals A exclusive NOR B, if two inputs are the same. Excuse me. Yeah, so the exclusive NOR gate can be used to check if two inputs are the same, which is a useful thing to do. Okay, so finally, finish off. It's sufficient, well, I'm putting to you that it's sufficient to use NAND gates to construct any logic function. And the reason for that is that if we can make any of these gates, right, using a NAND gate, then wherever we see a NOT gate, an OR gate, or a NAND gate, we can replace it by its equivalent NAND implementation. So how could you do that? Well, okay, let's say you've got a NOT gate. Well, it turns out that, well, this is the truth table for a NAND gate. It turns out that a NOT gate can be created using a NAND gate with A on the input and a 1 on the input. Okay? And this would give you A prime. So how do I know this? So let's say input A is equal to, well, we've got an input A, and we put input B, we set that to a 1. That means that we're only looking at these two rows. All right. So we set B to 1. Well, then if I put an A as 0, then the NAND gate will give me an output of 1. If I put an A as 1, the NAND gate will give me a 0. So if I have this arrangement here, this is exactly equal to an inverter. So that's the inverter taken care of. We've already seen how we can do an OR gate. So the OR gate, if I have a NAND gate here, I just put in an inverter, which is really this thing, on the inputs, right? So this gives me A or B. And over here, you can already probably guess how I can make an AND gate out of a NAND gate. So I've got A and B here. This is the NAND gate. How do I turn A NAND B into A and B? What do I need to do? I just need to re-invert the output, don't I? So this gives me AB. And that inverter we can construct using another NAND gate. Okay, so that's a relatively simple way to show that each of these gates can be replaced by a NAND gate. Well, because you can construct any logic function out of these gates, logically, the pun intended, you can construct anything out of just NAND gates. Now, if that's the case, what happens is when you can buy custom arrays of NAND gates to construct any logic function that you might need for a particular microchip. So let's say you wanted to construct a function here. You might put A into here. You might put B into here. And then you can then construct pretty much any logic function using different combinations of inputs. So you might have CD here, and then these two inputs might go into something like this. And you might get some sort of function out here. Simply by connecting these arrays of NAND gates in any particular way, you can get any function that you desire from the inputs. So this makes it a lot easier than constructing individual AND gates, OR gates, and NOT gates, trying to put them onto a microchip in very specific places. That's okay if you're building something that you might make millions of chips, because you can afford to spend money to get that right. But if you're prototyping something, so you just want to construct a quick circuit that's you're going to be using in low quantities, then you can buy gate arrays. So these are called gate arrays. And you can do this a lot more cheaply than trying to construct everything from scratch. So in practice, this is what we do for a lot of prototyping applications. Okay? Okay.